Tales of mechanical beings date back to ancient times. For instance, the myth of Talos depicts a colossal bronze man built by Hephaestus, the Greek god of invention and blacksmithing. Tasked with safeguarding Crete, this bronze figure patrolled the island 3 times a day, hurling boulders at enemy ships nearing the coast. In the medieval European and Islamic world, devices like Al-Jazari's automata, including water clocks and programmable machines, showcased early engineering prowess. One of the greatest pioneers of the Italian Renaissance, Leonardo da Vinci, sketched designs of a mechanical knight capable of limited movements, foreshadowing today's humanoid robots, and a mechanical lion. So, the idea of robots and the robotics field is not new. People have been fascinated with them for a long time. It's a true phenomenon in pop culture that has captured the imagination of previous generations. So, what's different today? Rapid technological advancements, and mainly the incredible growth of AI, are making possible the creation of intelligent machines, which we could only imagine and depict in movies in the past. Robotics is the branch of technology that deals with the design, construction, operation, and use of robots. Machines that can perform tasks automatically or with human-like capabilities. Let's break this down. Mechanical engineers are needed to construct robots' physical structures. They are responsible for designing and constructing robots, including their mobility mechanisms. Electronics and electrical engineers design systems that enable the robot to operate and control its actions. While electronics power the system, various types of AI drive the robot's decision-making and behavior. Robots are equipped with various sensors and cameras to collect necessary data and perceive their surroundings. This is how AI developers and engineers pitch in. So, this truly interdisciplinary field requires specialized skills in several distinct areas. Like other types of AI, the robotics domain is inspired by human capabilities. Robots are designed to mimic and augment human abilities. To achieve that, researchers use a multidisciplinary approach combining different AI technologies. Typically, we should consider a system with multiple models instead of a single model that does it all. For example, an autonomous robot might use computer vision for object detection and environment understanding, simultaneous localization and mapping for navigation and mapping, reinforcement learning for decision-making, and a natural language processing model for understanding and generating human language. Combining all these models allows a robot to perceive the environment, make decisions, communicate with people, and act accordingly. Let's point out several intriguing use cases. You probably know that under the direction of Elon Musk, Tesla is building a Tesla bot, which is described as a general-purpose robotic humanoid. The goal is to create a robot that can relieve humans of dangerous, repetitive, and boring tasks in logistics. For example, a Tesla bot could help with factory and warehouse work, moving and stacking boxes, counting and auditing inventory, and lifting weights. And it's not just Tesla. Many companies develop their own autonomous robots and contribute with valuable research. Medical robots are a fascinating use case already in the mass adoption phase. These robots can perform incredibly accurate medical interventions and even complex surgeries which save lives. There's so many amazing innovations that are becoming mainstream. Self-driving cars, harvesting robots, cleaning robots, space robots, search and rescue robots, security and surveillance robots. The future is here, and AI is at the forefront of all of these innovations. IBM defines computer vision as an AI field that uses machine learning and neural networks to teach computers to derive meaningful information from digital images and videos. Consider this analogy. If AI functions as the brain, computer vision serves as the eyes, As humans, we effortlessly understand our surrounding environment with all its nuances. We can distinguish moving objects, changing shapes, and different colors. Sometimes we can notice the slightest differences and the most subtle details. The study of computer vision is a monumental effort to develop sophisticated AI models that allow computers to comprehend real world information. To do that, computers consume input through images and videos. Images are simpler because they capture a single moment statically. Conversely, videos are more complex, appearing as continuous sequences of images, for example, 30 frames per second, that require processing. The computer must analyze each frame and understand its context and continuity. There are four main families of computer vision models. First, we have convolutional neural networks. CNNs are foundational for computer vision because they are great when working with high dimensional data. In the early days, AI researchers used other types of neural networks for computer vision problems, but they struggled with high dimensional data images due to the immense number of parameters required. In contrast, CNNs are great at capturing spatial hierarchies in images. But what does this term mean in plain language? It means that CNNs are great at organizing the elements in an image based on their importance and depth. Imagine looking at a picture where some things seem closer to you and others farther away. The foreground is up close, the middle ground is between, and the background is distant. Larger objects often appear closer and more significant. Overlapping items make those in front look nearer, and centered or top positioned elements typically attract more attention, enhancing their importance. CNNs are effective at processing information due to their layered structure. This enables the network to learn basic features, like object edges in initial layers, and progressively capture complex, high-level features, such as shapes and objects, in deeper layers. Next, we'll focus on transformers, a key topic in our upcoming discussions on generative AI. For now, we can just say that, in some cases, AI researchers apply transformer architecture to images for the purposes of computer vision. Third, generative adversarial networks, GANs, primarily create lifelike images. Lastly, specialized networks, like UNet, excel in medical image segmentation, while EfficientNet optimizes performance by efficiently scaling neural network dimensions and utilizing computational resources. Computer vision has a ton of exciting real-world applications. Self-driving cars, medical imaging, security, surveillance, and other areas we previously discussed show great promise in robotics. It's important to remember that computer vision does not need to be part of robotics to be an incredibly useful product. For example, consider face recognition software. It's just a model built into a software product without a robotic body. Some of the most exciting advancements in computer vision are currently in virtual reality, revolutionizing such industries as education, entertainment, and long-distance communication. In our next lesson, we'll discuss traditional ML methods. Products like ChatGPT, Tesla's self-driving cars, and robots make the headlines. But we should remember that the more significant portion of the value created by AI today is related to less flashy business use cases. Financial institutions use machine learning to detect fraudulent activity or predict a customer's likelihood of repaying their mortgage. Insurance companies use ML to offer more precise pricing for life and non-life insurance packages. Machine learning allows retail companies to predict demand and optimize their orders. E-commerce giants like Amazon optimize pricing and conversions through ML algorithms. They can also predict what product you'd like to buy next based on previous shopping history. The list goes on and on. These and many other use cases have existed for over a decade. Very few businesses fail to benefit from AI. We should remember that while general AI is trendy and promising, the traditional AI applications I mentioned continue to impact businesses and deliver significant value. ChatGPT became a global phenomenon upon its release, sparking widespread excitement about AI's advanced future potential. And the branch of AI behind impressive models like ChatGPT is called generative AI. Generative because it can generate new data or content. The word generative highlights the system's ability to create something new rather than process existing data. Every conversation you have with ChatGPT is open-ended. The model, trained on extensive text data, generates new and unique real-time responses. Similarly, providing DALL-E, OpenAI's image generation model, with a detailed description will prompt it to create a unique picture tailored to your specifications. This illustrates the core capability of generative AI, producing novel content by leveraging patterns learned from trained data, a common feature among these models. But AI developers can use several different techniques to achieve generative AI, including large language models, diffusion models, generative adversarial networks, neural radiance fields, and hybrid models are also possible. I'll briefly describe each type of these generative AI. Large language models, or LLMs, are the foundational technology behind ChatGPT. I want to provide more details and give you a good foundational understanding of NLP, language models, and the development of models like ChatGPT. To grasp the workings and origins of this vital technology, we've dedicated the next 2 sections of the course to a detailed introduction. LLMs are neural networks trained on vast text volumes, learning to predict word relationships and the next likely word in a sentence. But more on LLMs in the next section. Diffusion models, like DALL-E, are advanced AI tools primarily used for generating images and video. During operation, DALL-E begins with a random noise pattern and progressively refines it into a detailed image, applying requested shapes and learned patterns through multiple steps to enhance realism. Generative adversarial networks, or GANs, introduced in 2014, are commonly used for generating text and images. GANs function by comparing 2 algorithms. One generates content, while the other judges its realism. Through this interaction, both algorithms enhance their capabilities, refining the content until it's nearly indistinguishable from reality. Neural Radiance is a specialized AI for 3D modeling, which emerged around 2020. And lastly, the increasingly popular hybrid approach combines LLMs and GANs into one powerful content generation system. Currently, there's an incredible amount of investment in different generative AI initiatives around the world, with the big tech firms leading the pack. It definitely feels like this is the key AI domain everyone's paying attention to. And how could they not? Generative AI can create and work with content in various formats, including text, images, videos, audio, data, code, design, and 3D. As technology improves, it will significantly impact the corporate world. Therefore, it will be highly advantageous to understand how it operates and how we can be at the forefront of this remarkable innovation.